Okay, good afternoon. So we'll start today with a reminder. We are entering the final stretch, and therefore course evaluations will be up and coming. And evidently for this semester, for the first time, we're doing them all electronically. So this is a new electronic feature. And what I'd like you to respond in a way that is useful to me. And one of the things I find really useful is if you tell me what you like in this course and what you therefore want more of. Okay? Because if I focus on what you like, then other stuff that you don't like, I won't have time to do it anymore. Okay? So it's a much clearer mandate to change the course. Some of you may think that these course evaluations, nobody ever looks at it. That's certainly not the case in my case, because I use these to affect the next time I teach this course, but also to change things around in the course and in the book. So this is a continuous experiment, which I find rather exciting. I try out new things. Some of them bomb, and you can say so. And in fact, when they bomb, I already noticed that they bomb, so I won't do those. But if you like certain things a lot, say so, and I will incorporate that in future courses. This course has gone, since I first started webcasting it, through an incredible metamorphosis, primarily based on students' comments. Okay, so don't think that nobody will read what you have to say. On the other hand, don't force yourself to write down stuff just because you think that the form has to be completed in some way. Only if you think that there's something useful, you should enter that. The second thing we'd like to do today, before we start continuing with Chapter 23, is work a little problem that builds upon stuff that we did last week, both electrophilic aromatic substitution chemistry as well as the Claisen condensation. And it's a synthetic problem where I'd like you to make this, I'd like you to start with this material and turn it into that using small carbon pieces, 3 carbons or less, to concoct what's on the right. So again, as in all of these problems, analyze first, look at the global picture, look at starting material, look at products. Okay? If you look at the starting material, you can see it's a bromobenzene. You look over here, you see that there's another bromobenzene, so clearly this piece reappears. And very quickly, this makes you realize that since we're starting with this piece, something has to be introduced here. Clearly, that's electrophilic aromatic substitution chemistry. So right there, you're already on the right track on solving this problem. The second aspect is to try to work backwards so you break things into smaller pieces. And you've already recognized that this bond has to be made by some kind of electrophilic aromatic substitution, so there's a retrosynthetic disconnection. And what's left over is this 4-carbon piece, and since the restriction is to have 3 carbons or less, we need to break this up into smaller pieces. Now comes in your knowledge of synthetic chemistry, and I'm going to build upon what we did last week, namely the Claisen condensation. There are other ways of breaking this into smaller pieces. There are many ways of solving this problem, okay? Particularly the construction of the side chain. But the quickest way of doing it is to do a retrosynthetic analysis here, because then you can start with an acetylbenzene, so this is a methyl, and over here you have an ester, okay? And the acetyl will be turned into an enolate, so this will be a negative charge here. This will be an ester. It's an acyl cation equivalent in that respect, and so the anion will attack and eliminate the ester function, the alkoxy of the ester, and that makes this bond. And so the rest of it is now a problem of solving the electrophilic aromatic substitution. On first sight, if that is what you're approaching it with, you would say, okay, this is just like an acylation. Okay, so if I have acetylbenzene, to make the acetyl, I just take bromobenzene and do a Friedel-Crafts acylation. The problem is, bromine is an orthopara director. Okay? So we'll only go to these 2 positions or to the para position, primarily to the para position, particularly with Friedel-Crafts acylation, where the attacking species is rather big. Okay? So we'll be directed to the para, which would mean this position, not that position. Okay? So we got a problem here of regioselectivity, and we have to now play some tricks with respect to how to solve the problem of sending the incoming acetyl group to the right position. In other words, we have to introduce a group that we then remove later on that will direct the acetyl to the meta position. And the only way we can introduce anything on bromobenzene is para, right? So there has to be some para function. Fortunately, we have one such thing. We learned that last week, and that's nitrogen. Okay? So we can approach this by nitrating at the para position, then reduce it to the amine. And the amine is now a much stronger orthopara director than bromine. Bromine is an intermediate orthopara director. Amine is a very strong one. The amine will control the game. And amine here will direct the electrophile here, and then you remove the amine by the chemistry we learned last week, namely make the diazoniamine and then treat it with H3PO2. So in a forward sense, so I didn't write out this time the retrosynthetic analysis because some of you said I should do more forward chemistry, so I analyzed it in words. Hopefully you got the gist of that. And in the forward sense, we would start with bromobenzene and do a nitration. Classic electrophilic aromatic nitration. The bromine sends the nitro to the para position. Then we reduce the nitro group while using our palette of reducing agents. I'm using H2 nickel, and that will give you the paramino bromobenzene. And this guy now controls the next electrophilic aromatic substitution. So now I'm going to come in and do an electrophilic acylation. Acetyl chloride, aluminum trichloride. Now, is there anything wrong with this, or is there a twist to this reagent at this stage with facing this stuff here? Anybody can guess this? Yes, electrophilic aromatic substitution is possible, but there's a much stronger nucleophile in this molecule, namely the amine. Okay? Amines react with acyl halides to make the corresponding amides. Not to worry. That means that in this process, we're going to make the acetamide of this nitrogen, which we can later on hydrolyze. So that's not a problem. In fact, the acetamide is a form of protected amine. So what we need to have, however, is 2 equivalents of this, because the first equivalent will be mopped out by the amine to make the corresponding amide. The second equivalent will do the electrophilic aromatic substitution. So now we're sitting here. And this is then hydrolyzed by the classical acid-catalyzed hydrolysis of amines. That gets you back your, of amides rather, that gets you back your amine. And then you treat this with sodium nitrite and acid. which is a source of HNO2. If you want to write HNO2, that'd be perfectly permissible. And that gives us the diazonium ion. And that diazonium ion we can reduce with H3PO2, a reducing agent that transfers a hydride to where the diazonium, where the nitrogen is, and that gives us the correct meta-substituted substrate. So we are almost home free. The last step is to do a Claisen condensation using, I'm using methyl acetate. You can use any acetic acid ester, but you have to watch out that you're using as the anion the alcohol that corresponds to the alkoxy group in the ester, and of course the solvent is the same also, and that indeed gives you exactly what you want, namely the product. Remember that the first product here is actually the anion, but it's understood that we're working up everything with acid or base, whatever is required, aqueous workup, to give you the corresponding neutral. So is that clear? Good. So this is a problem, by the way, I should assure you, because you may have been flustered by this bit here, okay, the two equivalents of acetyl chloride. I wouldn't serve that up to you, because it's sort of like a Trojan horse twist here that I'm sure most of you would miss, particularly in an exam situation. So that I would consider unfair, okay, so I won't do that. But I thought it would be nice to sneak this in here so you get an added twist. But you get the general strategy. Okay, so we've been talking about the Claisen product and related compounds, in which we have the a situation where we have two carbonyls flanking a saturated carbon, which turns the corresponding hydrogens acidic. And when we have this in an ester situation, that is 3 oxoesters, which can be either in the form of this guy here, which is directly, without the R group, directly derived from the acetoacetic ester, from the Claisen condensation, or we can do where we can start with a diester, where we have again a situation like that. These two units are used extensively in organic synthesis, in part because the simple derivatives, namely this being methyl, that is the Claisen product of methyl acetate, which was the first example of the Claisen condensation that we discussed last week, commercially available, is used extensively as a building block. So you buy it in order to do the chemistry that we're discussing now, and we started briefly something wrong with it, pointer. The chemistry we started last week. So remember that this oxoester could be alkylated at this position. So here's one alkylated product. And then we finished off last week by saying that part of the usefulness of these keto esters is that we can get rid of the ester group. So the ester group really is just an auxiliary. And it's an auxiliary in order to enable you to make an enolate at this position, which is relatively non-basic, so you can alkylate with secondary haloalkanes as well as beta-branched haloalkanes. Okay? Once you get rid of it, the net essence of this process is that you've actually alkylated the enolate of a ketone. When this is methyl, it's a methyl ketone. And this goes by hydrolyzing to the carboxylic acid, and then when you heat this up, you get decarboxylation. And you can see that the product is a ketone, where this R group was introduced by alkylation of this starting material here. So it's a roundabout way to allow you to do these alkylations without running into the age-old enolate anion problem, too strong a base, and things go to hell with respect to side reaction, namely E2. And a similar scenario occurs here with this diester, also common name is malonic ester. You can buy the CH2 type compound, you can alkylate, and then you can alkylate twice, and we'll see that in a minute again. And then you can hydrolyze to the dicarboxylic acid, and we have again a situation where we have a COOH, where in the beta position there's another carbonyl. Of course, the two are equivalent, so I'm just focusing on the left as being the one that feels that it has to take off, but it could be either side, 50-50, right? And so this guy just focuses on this carbonyl function here and realizes it can kick out carbon dioxide. And what's the product? The product, if you look at the topology, is actually an acetic acid, okay, which has been substituted by R. Okay? So it allows you to make substituted acetic acids. And the way this decarboxylation works, as we did at the very end last week, is that this carboxylic acid lines up such that the proton lies right opposite the 3 oxo group in this array. And you can see that when it does that, you have a 6-membered ring type of scenario, pseudo-ring scenario, where you can move 6 electrons around in an aromatic transition state. And so the way I've written it here is this electron pair goes out, plucks off the proton. As the proton transfers from this oxygen to that, this double bond goes in here. And this, of course, as soon as this single bond, this electron pair goes in here, as soon as this starts to happen, that green guy, the leaving group, carbon dioxide, recognizes, hey, I can be carbon dioxide, and just kicks out this electron pair in here, in part facilitated by the fact that this one is moving out, and therefore it's pulling on this side. To put it differently, everything happens all at once. Okay? They're all communicating, and the net result is that carbon dioxide blows out. The initial product is an enol, which then goes to the keto form. Of course, from this particular material, this is a useless reaction. You get acetone out of this, right? And you're destroying the carefully constructed Claisen product. But if you have alkyl groups here, R1 and R2, then it means that you're making a substituted a methyl ketone derivative. And that's what we'll see examples of that in the following. Okay? So here's an example of decarboxylation. Decarboxylation is classic, nothing new. Hydrolysis followed by heating. And the hydrolysis can be done with under acidic conditions or under basic conditions. In this case, the literature reports sodium hydroxide. Actually, most of the literature does both, and then they settle on the one that gives them slightly better yield. So both of them are usable. Okay? Sodium hydroxide would, of course, hydrolyze the ester to the carboxylate, and then you protonate to the carboxylic acid. And when you heat this was done in boiling water, therefore 100 degrees, carbon dioxide blows out. Okay? And what we have here, we have a ketone, or an acetone, if you wish, where one of the carbons has been substituted by this group here, which was originally introduced through the corresponding Claisen product, enolate anion. So we are sacrificing this ester, we're throwing it away, and we're using it simply to allow the alkylation, and in the end, that's what we want. Okay? So retrosynthetically, if you are given the task of substituting acetone with a butyl group like this, think of acetone as being the corresponding Claisen product, because we can get rid of the ester by decarboxylation. Similarly, with this diester, we're introducing this. This is now the branched example, and this works very well, no elimination. And then you, in this case, the literature did the acid-catalyzed hydrolysis. When you do the acid-catalyzed hydrolysis, you get directly the carboxylic acid, and then you can just heat it up. In fact, you can just do everything in one step, hydrolysis and loss of CO2, as these guys did. Just heat it up with aqueous sulfuric acid. It makes the carboxylic acid. The heat causes this to kick out carbon dioxide, and you get this product here, which is nothing else but a substituted acetic acid. So retrosynthetically, if you see any substituted acetic acid, meaning any carboxylic acid, you can cleave at the acetic acid carbon, at this carbon right next to the carboxy, and think about introducing the whatever else is hanging off there, whatever else the substituent is, introducing it, starting with a malonic diester or propane dioate ester by alkylation at the central position. That's the beauty of this methodology and these building blocks. So here it is again. We're starting with the Claisen product, and we can alkylate once, and then we can alkylate twice, and then we can hydrolyze and kick out CO2, and there's the product. So this is the generic picture, which you could look at from left to right, but it's more useful to look at it from right to left. And imprint into your brain the picture here of a substituted acetone, where we have substituents on one carbon. Notice that the beauty is not only that we can introduce all kinds of alkyl groups without fear of elimination, but also that it's the same carbon on the acetone. If you were to try to do this with acetone, all hell would break loose, right? Because with acetone, you make the enolate, you introduce one alkyl group, and then the second alkyl group can go into either side. Okay, so you can either give dialkylation on one carbon, or it starts going to the other carbon. So this way, you control where the carbon is, because this is clearly the more acidic carbon that's being alkylated. So here's an example from the literature. So here they use sodium methoxide and bromobutane that introduced the butyl group, and then they hydrolyzed base with base in this case, and then acidified and heated to 100 degrees to get 60% of the corresponding substituted acetone. Okay, of course it's a, what is this? This is 2-heptanone. Okay. Or you can alkylate again, more base, another, and so in this case they needed the dibutyl compound, so the butylate again. So now you have two substituents, and you hydrolyze, heat, decarboxylate, and now you have a dibutylated acetone. Okay. Using words that drive home the retrosynthetic picture and how to view this particular molecule. So the bottom line is, if you see a ketone, and we now have several ketone syntheses that are available, if your starting material is a ketone, and in the product it looks like we've introduced alkyl groups into the starting material, one way to approach this is through some Claisen type scenario where you have a sacrificial ester function that will do that for you. So similarly, if we do the propane dioate ester analysis, this is acidic, and we can alkylate once, and we can alkylate twice, and then after hydrolysis and decarboxylation, we have a dialkylated acetic acid. So again, if you have a starting material which is either acetic acid or a derivative thereof, and you need to introduce alkyl groups, or you need to make a compound that has substituted acetic acid pieces at the alpha position, that is the way to go, or one way to go. That is rather simple, because it's simply enolate alkylation chemistry. So here's an example starting with this methylated species. They introduced bromodecane, and then they hydrolyzed and decarboxylated, and that introduced this decyl group alpha to what, from this perspective now, is the propanoic acid. Okay? Or to put it differently, since this group was introduced from the malonic ester, or the propane dioate, if you start the propane dioate, you methylate once, alkylate again, and you get an acetic acid that has a methyl and a decyl group stuck into them. More useful, as far as I'm concerned, is to look at this retrosynthetically. The beauty is you can cleave both. You can cleave two CC bonds at the alpha position of a substituted acetone or a substituted acetic acid, and that, of course, gives you tremendous simplification of a potential target, and you can approach it using these commercially available pieces. Now, these enolates, they behave just like ordinary enolates, okay? It's just the beauty is that they're not basic, okay? So we can not only alkylate or treat with oxocyclopropane and do similar things, we can also do, for example, Michael additions, okay? So if you take the propane dioate species, and here's the molecular model, here are the two ester functions, here's the CH2 group that can be deprotonated to make the anion, that anion will undergo Michael addition. That is, it will attack the beta carbon of an alpha-beta unsaturated carbonyl, just like in the Michael additions of enolates, okay? Or ordinary enolates. Ordinary, I mean, yeah, okay, so this is a special enolate because it's relatively non-basic, but it's still nucleophilic. And so that means that you're making this beast here, where you've generated this new carbon-carbon bond. Okay? And of course, you still have the diester function. In the molecular model, it's more clearly spelled out. There's an ester, here's an ester. If you hydrolyze that with the dicarboxylic acid, one of them will blow out as carbon dioxide. Okay? So this simplifies the target structure to something smaller. And as we discussed in the sequitur to the Michael addition and enolate addition chemistry in the chapter on ketones, conjugated ketones, the corresponding products can undergo intramolecular aldol condensation, which is called the Robinson annulation. So this guy here, for example, which, by the way, you may recognize, this one we made last week by the intramolecular Claisen condensation.